noticed one day, Chris and Martin saw something strange. A little leaping lemur who liked to bounce and play. They followed their new bouncing friend, not knowing where this adventure would end. The animals were headed just around the bend. Where they going? I don't know. Come on, let's go. Me and you and Sabuna. Come along and see what's new. We're doing the things that animals do. New animal brings to see. Animal jumps is the place to be. Rooms are leaping. Wild dogs running and nobody's sleeping. Me and you and Sabuna. Come along and see what's new. We're doing the things that animals do. Me and you and Sabuna. Come along and see what's new. At Animal Junction, we're waiting for you.
Hey Kayla, let's go see what Mr. Mary's up to. Yeah, let's go!
We began this lab with the fish in a small beaker with 100 milliliters of water and poured increasing amounts of TMS into the water.
Our first dosage was 4 milliliters, then 4.6, 5 milliliters, 5.4, 6, 6.5, 11.5, 12.5, and finally 11.1 milliliters.
After each dosage of TMS, we stopped and took a 1-minute video of the fish, monitoring its breathing rate, movement, and other important factors that would possibly change with the amount of anesthetic present.
We first noticed that with more tretane methanosulfate present, the fish's metabolism dropped.
This led to a decrease in its breathing rate, movement, and loss of stability as well. Hey Alexa, look at the fish conveniently placed on the table so that we can show the class our fish tranquilizer lab.
Hey, let's go check it out. I know what. Why can't we just
We must have a message in our Snapchat inbox.
Yeah, let's go check it out. Hey Alexa and Kayla, my name is Benita Alfred. I'm from Toronto, Ontario. I'm doing a fish tranquilizer lab in biology and I had a couple of questions. What is a tricane methanosulfate? How does tricane methanosulfate affect the nervous system, and how does dosage affect a small fish? Hey, Benita Alfred from Toronto, Canada. Tricane methylsulfonate, also known as TMS, is used on fish for anesthesia, sedation, or euthanasia. It has the chemical formula C10H15NO5S. TMS mainly functions as a muscle relaxant that blocks the occurrence of action potentials that signal from the brain to other areas of the body, and therefore they're not being transmitted. It is considered standard practice to use anesthetic agents for humane handling of fish during stressful or invasive procedures. Usually this anesthetic is used to reduce stress of the fish when a person is performing surgery on it, but is also useful for the implantation of tags in fish and other fish-related research. If you look right over here, it's the formula of this anesthetic.
To answer your second question, Benita, anesthetics are used to sedate fish by depressing both their central and peripheral nervous systems. The entrance of sodium into the nerves is inhibited, resulting in the limiting nerve excitability. Nerve inhibition is facilitated by the lipid solubility of TMS, which allows it to move easily into the cell membrane to bind with sodium channels. Because of this process, voluntary movement and sensory reception is significantly reduced.
To answer your last question, Benita, Sommerfeld and Smith noticed the changes in behavior in fish with the increasing amounts of anesthetic, or TMS. At stage 1, there'd be a light sedation, slight loss of reactivity to external stimuli, and slightly decreased operculum rates. Stage 2, there would be a deep sedation, total loss of external stimuli, with the exception of strong pressure, and there would also be a slight decrease in operculum rates. At stage 3, partial loss of equilibrium would occur, loss of muscle tone, and hyperactive behavior, for example, erratic swimming, would also occur. There'd also be an increased operculum rate, reaction to only strong tactile or vibration stimuli. At stage 4, there'd be a total loss of equilibrium, slow and regular operculum movement, loss of spinal reflexes and reactivity. At stage 5, there'd be a loss of reflex reactivity completely. And finally, at stage 6, the fish would experience asphyxia, where the operculum movements cease completely, and cardiac arrest would be the next step.
You know what? Maybe we can explain it better if we actually do the lab.
Yeah, but we'll need some help.
Zaboomafoo!
Hey Kayla, hey Alexa, what do you guys need help with?
We're doing a fish tranquilizer lab.
I know all about it. I think that an increase in tricaine methanosulfate will gradually slow the basic systems found in the fish's body, including its breathing rate, movement, and stability. We need a couple of materials, including distilled water, 2 beakers, plastic pipette, a graduated cylinder, a goldfish, and tricaine methanosulfate. As for the methods, you first have to obtain a small fish and 100 milliliters of water. Record approximately 1 minute of video footage. Next, add 4 milliliters of 500 milligrams per liter to your fish. Record a 1-minute video. After each increase of tricaine methanosulfate, record a 1-minute video. So you'll repeat step 2 with 4.6 milliliters more, 5 milliliters more, 5.4 milliliters, 6 milliliters more, 6.5 milliliters more, 11.5 milliliters more, 12.5 milliliters more, and finally 11.1 milliliters more.
At 0 milliliters of TMS, the fish's breathing rate is normal. It has not yet lost its balance, and the fish is swimming at a normal pace. A normal fish's breathing rate is 99 to 120 breaths per minute.
Between 4 milliliters and 6.5 milliliters of TMS, the fish's breathing decreases slightly, but increasingly gasp for air after each dose of tricaine methanosulfate was added to the beaker with the goldfish. Ironically, it swam faster during this period of time.
At 11.5 milliliters and 12.5 milliliters of TMS, the fish's breathing continues to decrease as it continues to gasp for air. There's also a significant drop in the fish's movement, as seen in the following videos.
And finally, at 11.1 milliliters of TMS, it is here the fish shows the most dramatic effects. Its movement is extremely still and it even begins to topple over. Thus, we decided to end the experiment as to not harm the fish. Wow, that was really neat.
Yeah, I agree. Hey, look, a call from Jen.
Maybe we could share our bio results.
Yeah, totally.
In the first few dosages, we noticed that the fish was moving very, very fast, and the breathing rate was increasing. But in the last few dosages, the fish wasn't moving around as much. There was minimal movement. It was sinking down to the bottom as it was trying to reach the top. And at the very last dosage, the fish started spinning and spinning and fell all the way to the bottom. But our fish didn't die. Our fish was a survivor.
Wow, Jen, that sounds a lot like our results.
Yeah, thanks for all your help.
Stop it!
Oh my gosh, Kayla, wait! What if we recorded too soon and the TMS had not been yet metabolized by the fish? Or during the experiment, we may have not measured the exact amount of TMS required, or the sample of TMS might have been contaminated, or we didn't add enough TMS to see a significant result?
That's what we call sources of error.
By using tricaine methanosulfate, we were able to see the effect that varying dosages of this anesthetic had on fish.
Increasing amounts led to less response to stimuli and lowered the fish's metabolic response.
When compared to our hypothesis, our prediction was accurate.
Despite our fish almost dying from the excessive amounts of TMS, there's an optimal amount of this anesthetic that can be used depending on the fish's size, environment, and sex.
It plays an important role in laboratory research and has become an essential substance in handling fish. See you guys later.
Bye, guys.
These animals are friends of mine, from the tip of their toes to the tiny behind. All the recordings we did to this day are time-consuming in every way. We all got our own mark, but we keep it in the dark. Thanks for dropping by, we're glad you came. This bio class, yeah, it's so fun. Come on, join in everyone, 'cause there's one more thing we have to say. Very good,